Hello, I'm Zeng, and I'd like to welcome you to Fantastic Gases. Today, we shall be discussing the absolutely fascinating topic of gas laws and their applications in transportation. Today, we'll be going over such laws as Boyle's Law, Charles' Law, and Gay-Lussac's Law. Now, first, in our great lineup of gas laws today, we're going to be speaking about Boyle's Law. Boyle's Law was discovered by Robert Boyle in the year 1662, and simply stated, it goes as follows. When the temperature is constant, the volume of a given amount of gas varies inversely with the applied pressure. So, what does that mean? Well, first of all, remember that in order for this law to apply, temperature must remain constant within the gas. So, for a given amount of gas, when the external pressure increases, then the volume decreases. Now, by how much will it increase or decrease? Well, let's assume that the pressure doubles. Then whatever volume of gas there was initially will be cut into half. So likewise, if the pressure is reduced by half, then the volume will double. So why on earth is that, Anda, you ask me? Well, let me explain. Let's assume you had a container full of gas, and then if you applied external pressure onto it, then it forces the gas molecules together. When they're forced together, the collisions between the molecules the size of the container and each other are more frequent. Therefore, the pressure amongst the gas is higher. Now let's simplify this with an equation. So the volume, represented by V, is inversely proportional to the amount of pressure, external pressure, applied. Now this equation can be rewritten so that it is the pressure times the volume is equal to the proportionality constant. Now I bet you're thinking, how on earth does this apply to anything, Zeng? Well, allow me to tell you. In fact, allow me to show you. With a bicycle pump. Now, when the piston on the bicycle pump is pulled completely out, and there's no pressure being applied to this main cylinder here, and the volume is still at its initial volume. So when I double the pressure, and therefore it's halfway in the piston, when I double the pressure, then the volume in the main cylinder is consequently cut in half. So this inverse proportionality will apply to any amount of pressure you apply to the piston, inversely of course. Now, we're going to move on to Charles' Law. Jacques Charles is the person who discovered Charles' Law, and he was a French scientist. Now this law is regarding volume and temperature, which, simply stated, is as follows. When the pressure is kept constant, the volume of a fixed mass of gas is proportional to its temperature. When the Kelvin temperature increases, and so does the volume. Now, let's write out the equation for this law. The volume, once again, represented by the V, is equal to the proportionality constant times the temperature. Now, this equation can be rewritten as follows. The volume divided by the temperature is equal to the proportionality constant. In the year 1783, the Montgolfier brothers had their first public demonstration of their hot air balloon. So when the Scientific Academy in Paris heard about this, they commissioned Jacques Charles to make his own hot air balloon. Now, Charles decided to use hydrogen inside of his hot air balloon. He felt it was more suitable. There was much excitement over this new aeronautical development. For more than 2 centuries, hot air balloons were used as scouts during wars, to spy on the opposing side, as well as carry supplies. Nowadays, however, hot air ballooning serves more as an activity of leisure. So, how did this concept, this law that Charles came up with, bloom into inventions of our modern day hot air balloons? Well, let's use the example of water and air. Now water, as you know, is more dense than air is. So if we had air in water, the air will form bubbles and the bubbles will rise to the top. Therefore, the concept back then, the idea, was that if they could find a substance that was lighter than air, that was less dense than the air surrounding them, then man could float just like a bubble in the water. Now, let's have a little refresher on the density equation. That density is equal to mass divided by volume. So, let's remember that as the volume increases because the temperature increases, the mass of whatever gas you have will remain the same. So therefore, remember the density equation. If the volume is increasing and then the mass stays the same, then therefore the density will decrease. So for example, if we had hydrogen and you kept heating it so that the mass stayed the same but the volume increased because it was expanding, because a hot gas expands. And then eventually, because the density will continue to decrease, eventually it'll be less dense than the air around it, and perhaps even light enough to carry a gondola with it. So that's how the hot air balloon works. Now, these hot air balloons have no way of controlling their direction. In fact, most of the time, they would just be blown around by the wind. So very often, they'd have to be tied down with a rope tethered to the ground to prevent them from floating away. So eventually, there was invented the dirigible, or the airship. Now, dirigible comes from the French term to direct, so basically these dirigibles were steerable because they had propellers and a steam engine. Airships were immediately put to use for war, the height advantage of the air balloon as well as the benefit of being able to steer. They were also used as entertainment by the wealthy, who would stay upon highly luxurious versions of these airships. Now, the principles that were used in making the hot air balloon were applied for the airships as well. Now, these are both lighter than air. They function with the lighter than air concept. Early airships used hydrogen. Hydrogen, however, is highly flammable, as demonstrated by the Hindenburg disaster of 1937. Airships then began to switch over to helium, which, being a noble gas, was not nearly as flammable as hydrogen. And also the helium acts for structural support. Within the envelope, which is where the main helium is, they also have these balloon-shaped airbags called ballonets. Now they're filled with air, and since air is more dense than helium, they would either inflate or deflate these ballonets in order to help the airship in its ascent or descent. Finally, we're going to move on to our third fantastic gas law of the day, the Gay-Lussac law. Now this law was discovered by Joseph Louis Gay-Lussac. Now this is actually the man who published Jacques Charles' works. And he extended the research that Jacques Charles did, and he came up with his own law, which goes as follows. When the volume of a gas is fixed, its pressure is directly proportional to its Kelvin temperature. Now let's go in for a deeper explanation. Now let's assume we had a container, a rigid container, and we placed in it a quantity of gas. And so this quantity of gas, the volume, is fixed. It's not going to change. So let's assume then we heat up this container, and the gas molecules inside continue to move around faster when they're warming up, and therefore there'll be more collisions against the container and each other. Therefore, the pressure increases. So let's examine the equation for Gay-Lussac's law. The pressure is equal to the proportionality constant times the temperature in Kelvin. For those of you who are drivers, have you noticed that the pressure in your tires increases or decreases or changes at all when it's extremely hot or extremely cold? Well, if you answered yes to that question, you're lucky enough to have experienced the reality of this fantastic gas law. Because the amount of air in your tire is fixed, right? It won't change. Give or take the quality of your tires, of course. So when it's hot outside, the molecules within the tire speed up in their motions and they crash into each other and there are more collisions, as we discussed. Therefore, the pressure in your tire will increase. Similarly, have you noticed that if you travel a very far distance, your tires get really hot? That's because driving increases the friction of the tires against the ground, and this causes heat. So, what happens to the pressure of the tire when it's heated up? It increases, of course. So, we've had the chance to explore 3 different, equally fantastic gas laws. But now I'm going to talk to you about something that's almost 3 times as good: the combined gas law. So, we take the 3 gas laws we've learned, and we mash them up together to make one super equation. It's somewhat like the polygamous marriage of 3 rather fantastic people. So, let's shuffle around these equations. So we have here all the variables from the 3 gas laws that we've reviewed. And using these variables, we're going to make up the combined gas law equation. So, on the top, we have the pressure times the volume divided by the temperature is equal to proportionality constant. This, ladies and gentlemen, is the wonderful, fantastic combined gas law. Now, I know what you're thinking. When on earth am I going to have to use all 3 of these variables, Andy Zeng? Well, let me give you one prime example. The weather balloon. Now, because I send weather balloons up in the atmosphere, all 3 of the variables which we've discussed today change. For example, pressure, volume, and temperature. So, with the weather balloon, all the laws that we discussed today are in action. So if we were to calculate all the changes and variables that the weather balloon goes through as it rises up in the atmosphere, it'd just be much more simpler if we had one super equation as opposed to 3 rather fantastic but not as super as one equation. Whew, well, I think that's all we can handle today with fantasticness. Go out and explore the fantastic world of gases. I'm Andy Zeng, and join us next time for a very special episode on the components of flatulence.